Hi boys and girls, today we're doing plate tectonics with graham crackers and pudding. We need to review a few things about Earth's layers. Remember last week when we studied the egg model that the Earth has a core, and the core is inner and outer core. We have mantle and we have crust. This week I'm going to pop in two new words, lithosphere and asthenosphere. Lithosphere is the crust in the upper mantle. It's rigid and it's cracked. So if you took our hard-boiled egg and you cracked it, those little pieces form plates. That's lithosphere. The upper part of the mantle that's really soft that the lithosphere floats in is called asthenosphere. So in our model today, we're going to be using pudding to represent the asthenosphere. And for the lithosphere, we're going to be using Rice Krispie treats and graham crackers. I have two different things to represent the lithosphere because there are two types of lithosphere. The oceanic crust is made from basalt and it's really dense, and continental crust is made from granite and it's less dense than basalt. The difference in density causes different features to be formed when these two types of plates interact with each other. So the plates, the pieces of lithosphere, think about that hard-boiled egg again, the little pieces of the hard-boiled egg shell would be a piece of crust, right? So those plates interact with each other. Where two plates come together, it's called a boundary, and we have three different kinds of boundaries. The first one that we're going to talk about is convergent boundary, and that's when two plates are coming toward each other, converging. The second kind is divergent boundary, and that's when two plates are moving apart. The third type of boundary is when two plates are sliding past each other, either in the same direction at different rates or in opposite directions. All right, so we're going to model what happens with these different boundaries, what kind of geologic features are formed with our pudding model and our graham cracker model. The first one that we're going to do is when two continental plates come together. For this one, I'm going to be using graham crackers to model two continental plates coming together. They're going to have the same density. And we are going to soak one end of the graham cracker in some water just for a second to make it a little soggy. And then we're going to put our continental crust down in the asthenosphere. All right, David, I want you to push them together. Take the ends and smush them together. All right, yep. What formed here? What does it look like? If you have two come together, same density.
Car.
It's a mountain.
No, it doesn't.
Here is the two plates. They come together, they're converging, and if they're the same density and they're continental plates, they form a mountain range. Okay? So I'm going to take that off. It's kind of messy there. And now we're going to model. We're going to model we're going to call this one continental crust, and we're going to call this one oceanic crust this time. So we're going to set them down here in our pudding, which is our asthenosphere. All right, so I want you to push them together. There you go. So the oceanic crust, which is made from basalt, is more dense than the continental crust, which is made from granite, and so it sinks underneath. So I'm going to use a fist to represent the continental crust and my flat hand to represent the oceanic plate. And when they go underneath each other, you form a deep sea trench, and then it melts, and then you get a bunch of volcanoes up here. So if you have continental and you have oceanic plate coming together, the denser oceanic plate sinks, you form a deep sea trench, and you form volcanic mountains. So if this was the Earth, you would get a mountain range here of volcanic mountains like off the coast of California, Pacific mountains out there like Mount Shasta, Mount Rainier. All right, so that is continental and oceanic, and this was two continental plates. Remember, they just form a mountain range. Now, if you have two oceanic plates that come together, the one that is older and colder is going to be more dense, and it will sink under, and you get a deep sea trench, and you form island arcs. Island arcs, like the Aleutian Islands. So there'll be some volcanoes that erupt up and form an island chain. The Aleutian Islands is an example of that. All right, so let's do divergent now. Remember, divergent is when two plates are moving away from each other. All right, so David, let's I'm gonna use this, kind of smooth it back out because it kind of got messed up there. Smooth this out a little bit here, and then we're gonna put these in. And what I want you to do, David, is I want you to push down and out. Okay, so we got a little bit of a ridge formed here, and in the middle of the Atlantic Ocean, there's a mid-ocean ridge that forms there. It's a volcanic mountain range that magma comes up and fills, and this is what makes the world plates move. So this magma comes up, pushes the ocean plates away from each other, and then when they get to where the continents are, they subduct underneath, and then they melt and recycle over and over again. So Alfred Wegener knew that the continents had moved, he just couldn't explain it. Harry Hess is the guy that figured this out. He discovered the mid-Atlantic ridge. All right, so again, when it's divergent, the plates move away from each other, and you get a little ridge there. Another place where there's a divergent boundary is in Africa. The Great Rift Valley in Africa is an example of two continental plates moving away from each other. All right, so that's divergent. Remember, Rift Valley, mid-ocean ridge. All right, so the last kind that we have is transform boundary. An example of this is the San Andreas Fault in California, where all the earthquakes happen. All right, remember, transform is when plates are moving past each other, either in the same direction but at different rates, or in opposite directions. So we're going to do opposite directions. So I want you to move one this way and one that way, but I also want you to press them up against each other so they snag with each other. A lot of force and pressure. Okay, and if we do it really violently, like an earthquake, you could crack up a bunch of stuff. Well, there we go. And you can hear it grinding there. So a lot of energy is being released, and rocks are breaking. And this I don't know if you can hear it or not, but I can. You can feel the pressure that builds up when you're trying to push them past each other. So bits of rock will break off, energy is going to be released. You're going to have a bunch of earthquakes. So California, San Andreas Fault, an example of a transform fault in the United States. All right, guys, thank you very much, and see you next time.